I'm happy to be here. I will talk about the Daphne compiler that I built over the last 2.5 years or 3 years. So yeah, I've already talked a little bit about me. I will just give a tiny bit of context that might explain why I try to cover so much ground. So I come from the city. This is maybe a most stark picture you can choose. So it's a very industrial city in Germany. It's a city of inventors, and I recently thought a little bit about it. I think it influenced me more than I thought. The bike was invented there. It is the bike where you still have to walk on, so you cannot pedal yet, but at least the concept was instantiated there. Also, arguably, the car was invented there. Mercedes-Benz, Carl Benz drove with the first car, basically not far from my home. So it's a very engineering focused city that still has a lot of factories and production, huge chemical factories, pharmaceutical factories, and so on. So I really like the engineering and tinkering aspect, and I admire big machines and complex processes and how they are integrated and make them actually work. So I really care about this. Another aspect is I studied in Heidelberg, and I also studied philosophy, cultural anthropology, and mathematics, which you can argue is much more abstract and beautiful in its terms of reasoning, and has less of this dirty practical details. So yeah, I try to bring both of these together and try to think in different directions. So I think it's necessary actually to constantly try to unify and synthesize theory and practice. I mostly talked about this earlier, so I will not talk about too much. I'm a member of the play group at UBC. I haven't said this yet. I'm also a co-founder of the Lambda Forge cooperative that is developing Datahike. And yeah, I have this long-term goal of figuring out actually kind of a cybernetic revolution for society, where you would have these tools that you will see in the following in a tiny setup, just sketched as kind of a massive collaborative simulation and reasoning tool and environment. Okay, so I already also talked about this, so feel free to interrupt me at any point. I'm really here for feedback. I also want to promote Daphne, and I think you should try to use it, but I'm sure you will run into issues, and I will try to fix them and help you with it. I'm happy to do so. But also on a higher level, I want to see basically where people stand and what they really care about conceptually, and then maybe develop the code base a little bit further into this direction to make it more useful. So yeah, why even care about this talk, and how to think about it? So probabilistic programming, I think, is one good way to have a kind of universal perspective on many different fields, and you can bring them together. Most importantly, statistics, AI, and the compositionality and the structured reasoning of programming languages. So what is an inverse problem, and why do you care about it? So on a very, if you want to pitch it nowadays on a very high level, you would say, okay, we all now know that there is the self-driving car use case, and this is here an example of a street scene in Cuba, in Havana. And first of all, you see that it's a fairly complex interaction between humans. You have all these school children crossing the street. You have occlusion. You have things you don't see. And you need to reason about, if you have to drive a car through there, how people relate to each other, what you cannot see, what are the latent factors in the world that drive the dynamics of the world, what you are uncertain about. It's a very complex inference process where you don't know a lot of things, and you are kind of uncertain about these things. So what you have to do is you have to kind of invert what you see into the abstract space into the model about the world that you have, to have an idea of what is going on and where you need to take care of, and what are potential dangers in this scene. So this is actually a fairly tricky problem. There are good reasons that we don't have self-driving cars yet, because you can argue that interacting with humans in traffic is kind of requiring almost human level intelligence. And it's very, very tricky to get this right. So if I would have to describe like a very high level picture about how does this, how you can view this, like you can argue about whether this is exactly what's happening, but I will take this perspective for this presentation. So what you typically can do in your head, you can, and also in the computer, you can write a simulation. So you will have some knowledge about or some idea of what the latent states of the world can be, and you will have some potential controls of how to also interact with the world that are literally under your control, like your body and things you can control with your body and through like talking to other people and so on and so forth. So then in the simulation, you simulate future outcomes. Could be forecasting, it can be prediction into the future. You can also have models that are not actually in time, of course, that just describe relationships between your concept space with the latent states and the actual outcomes that you care about. Now, what probabilistic programming is capturing is both the simulation aspect, but also the right-hand side, the inference, which is basically inverting this simulation process, which I will show you later. This you can represent this with general purpose programs, with Clojure programs. So assuming that you already know what the outcome will be, so you have data for this, you want to basically pull back this information and get an update, a belief update over the state of the world, the latent state, and also potentially how you can control the world and what would be good choices for this. So this is like the 50,000 feet view of how this relates to each other. Another motivation for probabilistic programming that we have worked on in our group is we took a specific simulator, in this case for pandemics, and took the data for Pittsburgh in the US. Took the simulation for Pittsburgh in the US. And then we choose the outcomes to stay under a certain ICU hospital threshold, and said, like, we want to know which policies conditioned on this threshold, on this outcome that we want to observe in the long run. How do we need to make policy choices so that we don't with high probability, we don't cross the threshold. So it's a probabilistic reasoning, because you don't know exactly how the world is evolving, and it's very stochastic on this level in the simulator. Okay, so the paper is down here. I will also provide the slides and add them to the Daphne repo later, so you can also look this up. Okay, so more concretely, let me talk about specifically probabilistic programming in terms of examples. So one confusion that I saw and that regularly pops up, at least when you interact with people from the programming language community, is that some people use probabilistic program to talk about stochasticity. And this is possible. This has historically been done, but I would like first of all say, if you want to simulate anything in your program and you're not sure about how the world behaves, in this case here you have a loop form, and this is the critical part here, is this sample statement that is here. So the loop, you will either recur and count up this counter if this value is true, or you will return I if it's false. So this is just basically running your program as usual in your normal environment. And the only thing that's different than typical deterministic program is that suddenly you have a source of non-determinism. In this case here, you explicitly introduce a random variable and draw a sample from it, like a coin flip. So this is introducing, or this is a stochastic program. Now, the stochasticity doesn't have to happen in this very explicit way. It can happen through many different, in many different ways. It can happen already implicitly. And if you think about distributed programs or distributed processes, you already have non-determinism just because of the way the world works. So if your machine is running multiple threads at the same time, you might not know in which ordering certain things will happen, and that introduces a stochasticity. And you can argue whether this is really in the world or not. But for you, it's really something you have to deal with. It's not something like, if you would ask me why care about statistics and why basically not just stick to like the normal computer science topics that are traditionally covered, I would say you have no choice. Like in many practical settings, you really have to deal with stochasticity and reasoning about what is happening, even if you don't want to. Okay, so this happens when we have stochasticity in our programs. Now, probabilistic programming actually captures something different, and it's not really in the name. So I've already hinted at this at the earlier 50,000 feet figure of the relation between simulation and inference. Probabilistic programming cares about inference, statistical inference. So it's automating statistical inference for you. So here I have, and by the way, sorry, just to, oh no. One thing that I should mention here, I will also mention this later. This loop, because of this condition, you don't know how many iterations it will run. I will talk about this more later, but it can have a non-trivial effect, the stochasticity on the control flow and the behavior of your program, even if it's like fairly simple code. So here we have a little bit more of a complex program. Let me walk you through. So here in the first, so again, like in Clojure syntax, and it matches also at least the Anglican syntax, not exactly the Daphne syntax, but I stick to Clojure because I want to pick you up where you are. So this is a sample statement that samples from a Gaussian distribution or normal distribution, depends on what the language provides you. So this is the traditional bell curve, and here it is centered on 0, and it has an expected standard. It has a standard deviation of 10. So like on average, you are 10 units away from the origin. So it's a very broad distribution if you want to think about this. Like it depends. Like you could just basically your knob to say how uncertain you are where the actual value of the mean is. Now, let's say you have a tiny data set of 3 scalar floating point data values, and you want to know what the mean actually is giving this data. So you can, in a probabilistic program, you can now just write a loop that basically iterates over all these data points. And then you say, you observe this data point under a likelihood. So here you say, actually, once I know the mean, I'm pretty certain. So I assume that it's very close to the mean, the data. And then you say, okay, I want to observe all these data points, and I will figure out what the probable mean was that kind of in this model generated this data, if that makes sense. So if you would think about it, you don't have an observe here. You would say that the data is basically being generated here. It's being simulated at this point. Now you have data, and this observe statement allows you to condition on this data. So this is the statistical conditioning. I will briefly touch base on this, but I don't want to I won't talk about like the statistical aspects too much in this talk. There's also like a book behind the compiler where you can read up a lot of stuff. I want to capture like the high level intuitions for you. So what has been helpful for me to talk to people who work on programming languages and have experience with logic programming is you can think of this as a form of soft logic programming. So you could say here, okay, normally in logic programming, you would say this mean has to be equal to this f. So you would have a strict equality constraint. You would say like, given that these facts are absolutely true, I want to know everything, for instance, from my database or from my logic program, what holds in the world where these data points are true. Now this is more soft here because you say here it's kind of a weighted form of these constraints that you can capture. So here you say like it has to basically be likely under this distribution here. So this is how you construct the likelihood. You say, okay, giving this mean, this data should be likely. If So what you would expect here, giving this data points, the mean should be somewhere between 6 and 8 or so. And you will get a distribution over all the plausible means that are properly weighted if you feed this into Anglican. So I should have actually created a histogram, I guess. I haven't done this, but it will just give you, it is also still a normal distribution. So this is a very simple model that you could even solve analytically. But just to give you the idea. Important also here is like these are, in this case, continuous spaces. So it's not so easy to just take a standard logic programming and bolt this on top by just weighting things. You really need to think about spaces where floating point numbers play a role. And that's already the point where there's a strong connection to data science, numerical computing, array programming. You really want to incorporate like the numerics into the probabilistic programming framework, which is not so much true for traditional probabilistic logic programming, which is another subfield that just cares about doing probabilistic inference on discrete spaces in extensions of Prolog or Datalog. Okay, so let me pause here for a second and ask whether anybody has conceptual questions, because I think it will be helpful to talk about them maybe here. Okay, I must be doing an amazing job. Okay, cool. So
I might have a question.
Okay, that's great. Hello.
So and I'm sorry that I'm not too deep into this, but I'm interested what kind of problems I can solve with this in your example that I cannot solve if I wouldn't use your library. Or in other words, what conclusions can you make from this program that are interesting?
Okay, so first of all, this program is for educational purposes mainly. That's one of the problems that I think. So there are problems with probabilistic programming. I can touch on those, but it only makes sense in some sense when I have covered enough ground. But I can already say that many of the examples that you still find, at least the traditional examples, often look like they are not really mapping to typical programs that you write. And that can be a problem. It's easy to shoot yourself in the foot. So probabilistic programming is still underdetermined in a sense that many of the inverse problems that you can encode are very hard to do. Many of them are actually NP hard. You can easily try to invert a cryptographic hash function in the code like this and just write it down. Perfectly fine probabilistic program, totally not going to work with any method you have because it's literally constructed so that it's not possible to reconstruct the values that create a cryptographic hash. So there are definitely like limitations that I can talk about. I've picked this example here that because it is easy to show basically how the different pieces relate, and this observe statement is all the magic. This is where all the hard work is happening, where all the compilation is for, and where all the inference methods kind of churn on to make this happen. So you can also think of it as running your program forward, and you really want to hit certain conditions at the point. So as I said earlier, and I think this is actually for my supervisor, kind of his current main sales pitch for probabilistic programming is actually taking simulators of the world, simulators like of the particle physics of CERN, like the big particle accelerator. This is one of the kind of most prominent projects that came out of our group, where you take this simulator, where you have an idea of how physics works, and you try to reconstruct what actually happened. Also, you only observe very tiny bits of, you have only a few sensors. There's so much happening in physics if you collide particles in the space where you do it. So it's very hard to capture a lot of this. So your signal is kind of sparse and you don't observe most of the world. And you want to reconstruct basically the state of the world and potentially then also derive like your own decision. So I would say like this here the way that you would traditionally do it, you would kind of do manual probabilistic programming. So what epidemiologists would do is they pick some parameters for the model and they run the model forward and they look what happens. And then they say, okay, these are too many cases. I should tweak these numbers. And then you go back and you kind of do manual inference. You tweak the parameters a little bit and you try to either find one set of parameters that are really good. So that would be kind of an optimization perspective. But what you want to do in general is you want to know basically the probability that certain parameter values that you choose, in this case here, for instance, social distancing rules, school closing rules, these were parameters that you basically controlled in this simulator. And it was just a config file that you start a simulator with. So you can have a very lightweight interface into an existing simulation code base. If you want to be very pragmatic and hook into things you already have. But this assumes you have a stochastic simulator that represents your knowledge of the world. I don't know whether this holds true in your setting. So basically what you need to come up with in general is a model of how to generate good synthetic data. That's the first step. You can think of generative testing. It's very related actually. So in generative testing, you try to cover all of the plausible things that could happen. And then in this case, you try to search for violations. While in the case of probabilistic programming, that's more general or inverse problems. You can condition on all kinds of things, not just on violating certain invariants that you want to hold. Was this somewhat helpful, or?
Yes, very helpful. So I can look at it. I can look at it essentially similar to where I would, based on my schema definitions, where I could simulate all kind of possible data sets that could be possible. I, in a way, could use this to sort of deduct a statistical distribution from it and limit it in some way.
Yes, you might have observed part of your database and you don't know the rest of it. And what it will give you is, if you have this model of how to generate databases from your schema, you can condition on the part you know, and then the question is like, how does the rest look like? Similar things, for instance, are done also in like knowledge-based completion, where you say like, okay, I have like DBpedia and I've observed all kinds of facts, and now I want to, it's a very sparse signal, I want to probabilistically infer whether two things are related to each other. And yeah, that is basically another problem where this holds. Okay, cool. Any further questions?
Thank you.
Okay. Cool. Okay, so we have introduced this form of soft or hard constraints, or more statistically speaking, statistical conditioning here. Now I will just mention this. You don't need to understand this. I think in the long run, if you want to engage with this space, it will be unavoidable. In some sense, to learn a little bit about how to write down probabilities and calculate expectations and pick up a bit of statistics. It's actually very beautiful. So the cool thing that is not often talked about of Bayesian reasoning is that it is very compositional. It's basically the only form where you can build models and have distributions and keep plugging them together and can extend your model. Well, if you optimize, the optimization is not compositional. So optimizing two things and plugging them together afterwards doesn't give you the joint optimum. You will have to re-optimize. And you see this also often in deep learning settings, where if you extend models, then you need to do end-to-end training of everything together again. So anyway, like Bayes' rule is kind of a very simple idea. It's basically capturing conditioning. I will not talk about it in too much detail, but I want to provide you the connection to the probabilistic programming part. So these are the latent variables, or the things you sample from, the prior that you have over the states of the world where you don't know what it is. this describes the relation of the forward simulation of the stochastic simulator. So if this is your latent states and y is your observables, then this basically describes the likelihood that you observe the data giving this latent choices, or you can also say X is your hypothesis of your latent space. And then you have to reweight by this term here. It's not important for the conceptual understanding here to understand this exactly, but this is the tricky part. To calculate this bit down here, you actually need to solve an integral in high dimensions. Integration is actually the tricky part. You can also, the way that I try to think about probabilistic programming more generally is as a form of, so you have differentiable programming, and this is a form of programming that provides you with forms of integration. So you will have to solve integrals in this setting. So this is where down here in the denominator is where like the hard work is to happen if you want to fit this. But I will ignore this for now. So this just gives you like the relationship in the inverse direction for your so-called posterior. So once you have incorporated this data y, you can have a new belief over what the plausible states of the world were where you put your prior. So typically you provide like a somewhat informed prior, but not too strict. Then you plug in the data, and the data will move your prior and update your belief and give you like a more precise. You have a more precise belief state of the world. So anyway, so you will require likelihood. Probabilistic programming does not strictly require this. So you can also have more general. These simulators don't necessarily define likelihoods. For example, the COVID simulator, you will have to either introduce those, or you can also use some more general setting with rejection sampling. But this is way beyond like what I want to talk here about. But picking this up and learning some of the statistics is extremely valuable to think in general about inverse problems. Okay, so now I want to make a distinction that's necessary to talk about Daphne. This distinction has been introduced by my supervisor. It's maybe like there are other ways to distinguish it, but I think it's conceptually in some sense helpful because it really is the basis for the specific way that the compiler works here. So you can split probabilistic programming languages and programs into two classes. You can have programs that you can completely unroll at compile time, and that makes your life much easier in a way. So this is what has been coined as first order probabilistic programs. So here is, by the way, the book. This is the book from former members of our group and my supervisor, Frank Wood. I highly recommend it. Unfortunately, I'm not sure how finished it is in the meantime. I think there are still some open issues that potentially need to be resolved. But you will find a very in-depth documentation, and I try to keep the compiler fairly closely to this book. So you can see this as a documentation for the compiler, which is very helpful for me because I wouldn't have the time to write this kind of high quality documentation. So in particular, I can just give you an idea why this might be worth it to look into. So here are, and it's actually written with Clojure syntax. So here are motivations, and then if you go down, there's like more in-depth description of probabilistic programming and different cool applications that have been showcased. And you see here that like the syntax is defined, and it's really defined in Clojure syntax. So it's actually a programming language design book written with Clojure in mind. And like, this is how you define like the syntax. This is how things are going to get expanded. And this is like how the compiler does this. And the compiler is faithful to this book mostly because it's built for teaching purposes. So it should be very helpful. It has like all these formalizations as well. So you have operational semantics in here. You can learn quite a bit also about programming language theory. So I would recommend at least looking a little bit into it if you want to dive into the compiler. I think it will provide a lot of valuable context. So anyway, you have this distinction. So if you can unroll and get rid of all the loops, then you are in this first order probabilistic programming land. And if you cannot do this, then you are in this higher order probabilistic programming land. And this corresponds roughly like to everything you can write down in a Turing complete language, including things where you don't know whether you are ever going to terminate. So this is kind of, if you have a good way to think about termination and can bound it, then you can kind of always try to get into this environment. And in many, like the typical way that even like numerical methods that work in this setting, like Bayesian non-parametrics, is being applied, is that it's often truncated, and you have actually, you kind of project it down into this part and another part that like captures the non-termination bits. So in general, it's a very helpful technique to break things down into a bounded context. So this is the example that I provided earlier for the stochastic program, and this already is not a first order probabilistic program, because this flip can be true arbitrarily many times. It's very unlikely, but it's possible that you cannot give it a fixed bound and say like this loop is only ever going to run for 10,000 iterations, because there's some probability that you will flip true 10,001 times or more, if that makes sense. Okay, but I think actually the first order probabilistic programming part is the most successful bit, and it's actually much easier to write like a lot of the inference methods. But first of all, like, let me talk about some of the higher order probabilistic programming languages that are out there. So there are nowadays, like the most prominent ones are Pyro for Python, which formerly has been developed by Uber AI. There is Turing.jl and also Gen.jl in Julia, which provides a very nice probabilistic programming environment. I would argue that if you really care about the numerics and the probabilistic programming bits and not so much about Clojure, that might be the better thing to pick up. I'm not a big fan of, I'm not a big fan of Python. So Pyro is fine. There are very smart people working on it, but if I would have to pick it up and I would have to give you a recommendation and you're not afraid of picking up Julia, which is actually fairly Lispy and fairly cool language, then I would recommend looking into this. And Anglican, where I'm also happen to be the maintainer for, also I don't do any kind of work except for answering for questions for people on Slack and on email. Anglican also fits into the Hopple language, and it kind of supports most of Clojure, which is pretty cool. It has a little bit, you need to lift, so like I have put a star because you need to lift like primitive functions that you want to use in Anglican explicitly into the Anglican context, and it has a few limitations with respect to higher order functions. So it's not a complete language, but it's close to it. While these languages typically support us a little bit better, and the way they do this is by tracing. So there are two different approaches. This talk here will be mostly about the compilation aspect in the Hopple case, but these languages, what they do is they run your normal interpreter and you run your Python script, and it will trace what kind of decisions you make in your program. And you can use this trace also to replay the stochasticity. So you have a way to replay like the random choices in your program, but you don't have you don't try to fully reason about what Python is doing and what's happening in the CPython interpreter and so on. It's kind of a very lean approach of embedding probabilistic programming into any environment. The same thing we have done basically with the epidemiological simulator earlier that I showed you. Is basically you just try to hook into the places where the randomness is happening, and then you have kind of a remote control where you only control what's happening in these places, and you try to steer the whole machine, the whole interpreter, so it does the right choices, and you figure out and run your inference. And the benefit of this obviously is that you can let people write arbitrary programs and use whatever like language features they want, and you don't need to understand anything about them. Anglican is a different design, and I think it's still fairly interesting, although it's became less popular to do a full compiler, But Anglican actually is a continuation parsing style compiler together with a particle filter library and sequential Monte Carlo and a lot of interesting inference methods that were very popular pre-deep learning. It basically, the Anglican failed at the lack of a good deep learning environment in Clojure at the time. And it was kind of hard to do anything against Python. Nowadays, we have like solutions for this. So if anybody wants to pick it up, I'm happy to help them. Like, it's not directly, so far I haven't directly done it for my research, but I think it's a beautiful code base. It's very educating. And actually, like, the Daphne compiler builds on top of this work. There's also, for instance, PyMC3, which is one of the more popular higher order probabilistic programming languages in Python. It's actually used by many people in scientific computing, and it is based on Theano, which is a static compile graph library for Python. So it can describe loop constructs, and you basically are in a higher order probabilistic programming environment, but it also does like this kind of compilation by explicitly constructing a compute graph in Python. Arguably, that's not really Python. You have like the TensorFlow / Theano like problems. But anyway, so this is like the high level space of other things. There's also Metaprop, which has been done for Clojure from the MIT group. Unfortunately, they don't ever cite our group. I don't know exactly why, but I find it a little bit annoying. Anyway, they haven't mentioned Anglican at all in their work. I'm not like that. I will point you to them as well. I think it's interesting. This is a trace-based approach that also exists in Clojure. It also complements Anglican and also like the Daphne compiler. And I don't have time today to talk about inference methods. Also, maybe I should. But a typical way you can think of this, I will just give you like a high-level sense of how you can do inference in settings like this, is you just run your interpreter and you run it a gazillion times. And the observations that you have on the path, you basically reweight each of the traces that you generate through the program by the probability that they have when they hit these observe statements. So it's like you have a gigantic shotgun with a gazillion of particles that you shoot basically through your program, and you hope that some of them are hitting the data, kind of giving it very high probability, and then you weight like all these runs that you have done. And that's kind of a very simple thing you can do to do Bayesian inference. It's also in some sense what we did with the epidemiological simulator. More advanced methods use more refined reasoning. But what our group has been basically doing, again, I will not talk about this here too much, except for later. I don't know, that's not true. I will talk about this. But our group has mostly used deep learning to improve like this approach and steer like these many traces that you run through your program and reweight them after with important sampling. You can read up in the book. Like this is mostly about the compiler, and I want to actually talk to you about the compiler design here and not about specific inference methods. So yeah, what the first order probabilistic programming languages, the most prominent one is Stan. It's actually heavily used nowadays in science, like in all kinds of studies. If you have to do Bayesian inference, I have a friend here who did his PhD in linguistics, who is using Stan to do his studies on how people basically pronounce certain things and how understanding is relating to pronunciation yeah. So on the JVM, I know the core developer is kind of a super nice guy, Avi Bryant. He's working on Renier, which is in Scala, and also has some compiler techniques. It's similar. It's kind of similar to Stan, but more for pure JVM solutions on scale-out clusters at Stripe. So he's working at Stripe, and this has been developed there. And yeah, so Daphne is also a FOPL, also captures the FOPL language from the book. And the way that it is done in Daphne, and I will show you this in a second, also in more detail, like in the code. But here you can see, like, again, let's say we have a probabilistic program like this. Again, we have like assembled our mean up here just for educational purposes, and we have like the observe statements here inside of this loop. What we need to do is we need to tell it the number of iterations of the loop. Then we provide here the bindings for the loop. So this would be like the data that we have. And then we have like all of the observe statements in this loop. There's also a loop for an accumulator. So these two things syntactically could totally change. They could also get closer to Clojure. But what you really need to know at compile time is you need to be somehow able to infer how many iterations there are, and then you will expand these loops and they will go away. This will be helpful. So Daphne is a FOPL compiler. It also provides a runtime. So there are some inference methods implemented. You can execute the code in Daphne. The inference methods that have been implemented were mostly implemented for course exercises. So they're definitely not production ready in that sense, but they capture the core idea and they at least return correct values in the unit tests that were necessary, like for the coursework. Daphne reuses the Anglican runtime, so there are sampling primitives and math primitives that you can pick, and you can use Daphne both as an AOT compiler and export the compilation artifact and run it in Python or somewhere else, as well as like in a Clojure context. And okay, so let me try to go into my Emacs. So well, maybe I should quickly ask for, do you have any kind of questions at the current state? Okay, then let me dive a little bit into the code for the fun of it. This is a cool thing that I can do with you that I cannot do in any academic context. There's no point in in looking into code. Okay. So how does it work? Let me first maybe talk about. So what I try to do, this is not the first compiler, or not the first at least compilation attempts that I did. So when I started to work on this, I decided that if you look in Racket, I highly recommend, if you look at programming language concepts, to take a peek at the Scheme and Racket ecosystem. It's very informative, and they have done a lot of work, and they're also super friendly Lisp people. They might not care about, they might not like the JVM or whatever, but whatever, like they definitely will talk to you, and they're super nice and help you to port some of the stuff. And this would be also some of the gaps that I see in Clojure, that we don't have that much compiler infrastructure available. We have some stuff. So anyway, like this analyze is similar to the analyze in the Clojure script compiler, or there's also an analyzer for Clojure. So this namespace, basically, literally, like I've put it here, you can see it defined on page 62. It really like tries to follow the semantics from the book. So the first thing that we do here is we lift some primitive procedures from the Anglican namespace and import this here, so we can use these sampling statements and other variables. It's not super important. Then typically in a compiler, like you have an environment, an empty environment, and also here I will show you this a little bit later, but we build up a graphical model. So what the compiler can do once it gets rid of the loop, you can kind of like expand the structure of the full program, which you can express as a graph. And this directly corresponds to probabilistic graphical model that I will show in a second. So here, these are just different helper functions of how to merge this. And then like the whole compiler is built, and this is so-called multi-pass architecture. It basically goes over the syntax on a specific level, and it dispatches on all the expressions and recursively walks over like the full syntax that you have. So here you can see, okay, I did this with multi-methods. I think it's particularly beautiful and kind of lean in terms of Clojure, what you need from Clojure. So here you can see that this is everything that describes the value, I will say, or constant. There's a constant, so this is how I dispatch on the which kind of operational semantics rule is going to be invoked. This is what is a Devon form that defines a function in the FOPL context. This is a let form, and so on, and sample and observe. So, and we have some collections here, and if it's not working, you should get an error. So what these analyze statements are doing, so you can see here, for instance, dispatching on a constant will basically just return an empty graph that has nothing in there because there are no random variables and nothing in this constant itself, and it returns the constant. And this row, I will not talk about here in too much detail. It captures control flow aspects and whether certain parts of the program will be active under certain stochastic choices, which you still need to do some bookkeeping for to have a proper probability distribution. It's described in the book, like the different trade-offs that you have there. And then the main part that I want to communicate to you, I try to break it down like in all these different rules that tell you how to deal like with a collection. So here you have like, you need to, for a vector, you just need to apply analyze to all the pieces of the vector, and then you will merge all the different the rows here basically when you return, and then you will apply merge graphs to merge all the graphs that collect the random variables and all the bookkeeping that you need to do, and you will basically return also like the return values of this, or the transformed form of the vector. And this is done for all the primitives in the language. So here is like, these are the most heavy ones. These are like the observe statements and the sample statements. So yeah, this is like one compiler pass, and this describes the actual core translation from Clojure syntax into a data structure of a graphical model that it's very easy to write inference methods against. And it's like the traditional setup that inference methods are being implemented against. So let's see, I can just show you what is coming out here. So, okay, if we just evaluate, can you see this? Okay, if I evaluate like 5, I will get an empty control flow. Okay, this is going away. So the first empty dictionary is like the control flow that is captured. The second is an empty graphical model. And the last thing is the actual return value. If we take this let, then we will get like this return value is 42. Now you already see that we have done some interpretation of the Clojure code, and the let binding went away. I will show you this in a second. That's actually kind of the special thing about this compiler is that it does very heavy partial evaluation. But anyway, so there are many passes in this code base, and I think in general this design is fairly nice. So I could just show you, let's say, desugar let. So we want to get rid of the standard Clojure let syntax. And what we are going to do, I won't go through like this here in detail, but it's the same thing. We say, okay, we kind of pattern match on the symbolic expressions and dispatch with this pattern matching up here, and say like, okay, we only care about let. We need to care about data structures because we need to iterate them, and everything else for this pass is actually unrelated. So we will not do anything on it. So this pass is much simpler. And by having these very simple passes that gradually transform the syntax that you have into the target semantics, into the target representation of your target language, the compiler is much easier to write. It's actually pretty finicky to do everything at once in like one pass. So there is now in Scheme, for example, there's the nano pass framework, which provides you with a lot of which allows you to write 50 or 60 passes or so for a Scheme compiler. Anyway, I think I should. How much time do I approximately have? I'm just asking to plan.
So we are just about 1 hour now. So no, I guess 15, 20 minutes.
Okay, I can do that. That's no problem. Cool. Okay, so let me talk briefly about partial evaluation. So this is the most heavy pass that is actually doing this hard work, and that might be useful also in another context. And actually, like, you could easily do this. You might know like of this technique as kind of constant inlining, and this is a very very brutal form of constant inlining, so to be very total. It basically tries to do whatever it can to get rid of any kind of expression. So you see here that it's applying the expression. It's applying multiple passes to the expression. It desugars the let. It partially evaluates. It tries to do a symbolic interpretation of the code, which basically just feeds the syntactic structure and applies like lookups. So you can, I think I can very briefly show how this is doing. So let's say here. So it looks whether things are, for instance, a vector, a map, or sequence, and it will basically apply like the operations on a symbolic object. So it will try to peek out something if it already knows that you're going to look up the third element. Even if the vector still is not evaluated, you can already extract the thing out of the vector. And obviously also, I should mention this only works like this whole language is in itself side effect free. So assume that you do the probabilistic reasoning in a context where you have all the data and everything in memory, and you do the computation. If you would have side effects, you could not do this kind of partial evaluation in this aggressive way. Anyway, so this is doing symbolic interpretation and simplification. And then we do desugaring, then we look whether we have actually reached a fixed point, and then we reiterate, because these passes might break apart pieces in the expressions that then can be further worked on by these other passes. Because the problem is, like with the let binding, if you think about it, I cannot partially evaluate this expression here before I have substituted this 3 into here for A. So I need to basically do this again and again, and there are there's functionality in the code base. So you can see here, basically this is an evaluator that does these things, and like here you get this broken down. So this is where all the closure gets erased, all the loops get erased, and it gets transformed into this data structure. Okay, I think this is the main bits that I want to show you, and I hope somebody has fun diving into this. And, I will switch back to my presentation. Okay, so the Daphne compiler, I just want to mention this, does a little bit more than what is in the book. So one problem that I had is, if this is a vector of a size that I know, then this expression is partially evaluated. I can evaluate this partially, but the semantics in the book doesn't actually allow this to happen. So I have extended it, and it was kind of necessary to build a linear algebra library, a small linear algebra library for this in the Daphne language, so that this can evaluate to a number, and then it can break. It can basically transform this for each form, and that makes it a lot easier to write some of the code, because you don't want to hard code the numbers into all of your routines for a specific instance of like matrix multiplication or whatever. These are the two methods that I implemented. One is Hamiltonian Monte Carlo. If you want to learn about probabilistic inference, I think it's a pretty cool thing to learn about. I can just give you, I provide these 2 pointers for you. It's definitely warrants its own talk, and has like, this is like a distribution here that you see in this banana shape. So the bluer the region is, the more probable is that you will sample from this space. And now you see that this is the dynamics that Hamiltonian Monte Carlo is defining and integrating over to draw a new sample. So it has this very smart way of defining a dynamic on this continuous space, and then kind of like evolving a particle along the space and drawing samples from there. And on this website here, you can play with different settings and how to actually do this this probabilistic inference. But I will not talk about it here much more. Also, like there is like this nuts sampler, which is actually the core piece. So Stan, the probabilistic programming language Stan, is basically built around this probabilistic sampler. You can see it expanding in both directions, so it is exploiting reversibility of the dynamics, and it's actually, yeah, it's very interesting to learn about statistical inference methods, I think, through Hamiltonian Monte Carlo, if you want to pick it up. And there is also a reverse mode automatic differentiation code in the code base. It's not very elaborate. Well, it is actually, let me put it that way. doing compiled reverse mode automatic differentiation is actually somewhat advanced still, and pretty cool. In this setting, it's easy to do because of the FOPL aspect. You don't need to care about loops and so on too much, and can unroll everything. But it's not, again, it's like a research code base. So I wouldn't rely on anything bigger for it. Like, you cannot train neural networks with it. That's what I'm basically trying to say. Okay, here's a paper that you can read, and this is like a general method that's also implemented. It's fairly slow, but it's something you can do. It's called Metropolis within Gibbs. It's a form of a Markov chain Monte Carlo sampling. Okay, so let me give an overview of what the code base was actually used for, because I haven't talked about this yet. This is so far just basically an implementation of what is in the book. So this is what I did, and you can read up the details in the paper. I think it will, yeah. So this is like in statistical standard notation, basically just a sequential sampling of variables, and then here we have like two variables that we actually observe. So if you draw this as a probabilistic graphical model, you've already seen in the code that there's this transformation into this representation. So the probabilistic graphical models, the white nodes are the things that you don't observe, the latent variables. And for x0 and x1, you have actually data in this case. So that's a synthetic example, but it's pretty hard to solve. So standard methods couldn't solve it actually. Or at least like the baseline method. Might be methods that can solve it. So what we did in this paper and with the compiler, and what a compiler provides you, because you have the structural knowledge about the actual program and don't just trace what the interpreter is doing without knowing what's actually going on. By having a full representation, you can take this, and we used a sparse inversion method to actually invert the structure of this graphical model. So this is an algorithm that you can just apply to the graph. And this is faithful because you cannot just flip the arrows in the statistics case, because you have something that's called, you get dependencies between the parents of variables if their child is observed. So here, once, let me see where this holds. So because Z5 gets inputs from both Z3 and Z4, there has to be a connection between these two parents, because once Z5 is fixed, the choice for Z4 depends on what you do with Z3. You cannot just freely choose them. And what we did is we used a very sparse, basically we try to make this as sparse as possible. And then we compiled this adjacency matrix, so you can represent this as a matrix, as a mask on top of a neural network architecture for continuous normalizing flows, which is a state-of-the-art amortized inference method basically for density estimation. So here we use it to plug it into this model that we got, and we learn this flow here on the right-hand side, which takes particles at time 0 and evolves them to particles at time 1, defined by like the intelligence of this neural network. So you try to fit it so that it steers the particles into the region where they likely came from, and you get your approximation of your posterior. And the cool thing is that this basically is much more efficient than if you would have fully connected matrices. So by using the right kind of knowledge about your problem, and basically you can boil down a lot of the Bayesian reasoning, all the tricks basically to solve inverse problems is you need to exploit as much structural knowledge of the problem to be actually efficient. It can be all kinds of forms of mathematics. So here we use this algorithm, and we use this amortization artifact. And it's actually being trained in Python. So we emit this, and then we create a Python class for this neural network code, and then we run this in this setup. So let me very briefly jump over, and then I'm practically done. So I just want to show this because I think it's so cool. Everybody in Clojure land should know this, especially if you do data science. I think it's pretty helpful. So there is this programming language that's called Highlang, which some people of you might have seen this. you can think of it as just a Lispy syntax for Python. It doesn't do anything to Python semantics. It's not really different. And you can directly basically translate it into normal Python code. So what I did here is I provided myself with a little bit of help, some way to translate distribution names to PyTorch names for the PyTorch library, and do some transformations. But the cool thing is that I can then, so let me go here. So there's this funny function. So what's happening here? You can see that I use this template form, which is basically using similar to Clojure macro expansion. It just allows me to do a little bit less of coding, uncoding. So this is actually Python code. And because Hi has the same syntax, I can kind of operate on the syntax in Clojure. I expand Python code in Clojure with this macro expansion, and then I just pass it to Hilang, and Hilang uses this and spits out a Python file. And I can use this Python file in whatever deep learning framework or whatever I want to use. So it's actually fairly easy to take pieces of Clojure code and compile them to Python if you want to, in this straightforward way, without having a full specification of Python and being able to translate this. So this is what I used. You can see here, like I invoke at the end the hi to Py function, and I do some translations. I need to like provide some environment. It's kind of minimalistic and very lean, so it's not a complete coverage of Python, and you won't be able to use this directly for your problem. But it's nice because you can really tailor it and solve your problem without having to accommodate Python as a whole. Okay, does anybody have questions about this? Because I think this might be actually valuable for some people to use.
Yes, thank you. So is Python used only for this deep network part and not for all the other parts, like the automatic differentiation and just this part, I guess?
It is used for automatic differentiation. I mean, there is an automatic differentiation in Daphne compiler, but it's not used here because what I do is I literally, so I can also show you how this result looks like. So this is this example that you saw earlier in the graphics. So this is what literally comes out of this compiler. It defines a class which is a flow model, which will be plugged into this continuous normalizing flow framework. And it just has three methods: sample, the likelihood method. So let me increase also. So these are literally these guys here. So I expand this code, and you can see it's fairly readable. And it is also possible to batch in here and have like batch processing. But this will run through PyTorch, and this code will be fitted with the PyTorch machinery. If that makes sense. So I literally only translate the program into this other representation for Python, and then I just use like normal Python machine learning. So from this point, Python doesn't know anything about Clojure.
Wonderful, thank you. So if I understand correctly, you may be saying that it could be generalized into a practical way to build PyTorch networks for general Clojure needs.
Yeah.
And the other thing you're saying is that possibly, actually what you built is not far from being pure Clojure, because this last part of the network, it could be converted to Clojure, hopefully, right?
Yes, it could be converted to Clojure. You would have to integrate. So the point is that this actually uses an ordinary differential equation integrator, a Runge-Kutta solver that is implemented in Python in PyTorch. So you would have to replicate this in Clojure. So one thing that I would find nicer, and I think that will allow much deeper integration and give the Clojure ecosystem, at least in the long run, more leverage, is instead of using Python, use like what the Julia ecosystem is providing. because these guys are really 100% into numerical coding and actually providing fast code, and really they try to cover ground that is not so much the emphasis for Clojure in a sense. So integrating these two, I think, would provide probably the biggest leverage. But I think you can also do it with Python. You could also live like, if you would not use like this continuous normalizing flow, you could totally also just emit like a normal neural network architecture. It has some way to match these distributions that is not a flow, and train this in with an MXNet in Clojure, or use libpython CLJ with PyTorch or whatever, and stay in Clojure. And I think this is something for the Clojure ecosystem, which probably is in some sense nicer integrated than this. But for research, and also to keep concerns separate and make debugging easy and so on, you see that this code is readable. This was very important to me, because if you make mistakes, and you will make mistakes, and there are subtle edge cases and things that don't exactly match, you don't want to have a big like chunk of one line wrapped in, like, I don't know, you don't want to have a ugly compiler output with munch names and stuff like that.
Thank you.
You're welcome. Okay, I think I can wrap it up. Okay, there are some other export forms. I mostly added them for the course because maybe I shouldn't say this here, but not many people are naturally into Clojure still. So many people who take the course on probabilistic programming, they haven't done Clojure before, and they just want to use Python, or they are allowed at least to use whatever language they want to use. So what I added for the course is a way to just export this graphical model structure, and then you can write your own inference method in Rust or in whatever language you want to do, with Julia or Python, or people mostly use Python, so we provided some support code for this. You can also just do some desugaring process. So this was for the, there are some Hopple bits in the language, in the repository for the course. And there's also like a continuation passing style transform, and even a Y Combinator transform, just because we had problems at some point in the course to provide all the proper like scoping and primitives in the target environment. So we did something that is somewhat inefficient and translated everything into Y Combinator. Just said people run the exercises and make it easy for them, and have no binding except for lambdas in the target language. Yeah. So next steps. And I'm really helpful if you can give me some feedback on this, because my PhD requires for me to work also on other things. So having a way to prioritize is helpful. It's definitely important to solve real-world problems, and this code base so far was mostly a research prototype, and it's like tested on research problem. We did like a bigger neural network inversion, which is kind of cool. So we took a classifier and inverted it with the same machinery for the paper. So that was a bigger model, but we already hit, like, at least with the flow stuff, some obstacles at the time that probably are like, at least are partially addressed by now. But anyway, that's not topic of this talk. So real world problems would be interesting if you have some and say like, okay, I really want to encode this, and this is very valuable. Yeah, we don't handle discrete variables in this amortized flow setup. So amortized inference, I think, amortized inference means you spend time, my supervisor coined this as inference compilation. You spend time on training a neural network beforehand to do this approximation later for you, by basically generating all possible synthetic data that you can imagine and training the network to do the inverse job in general for you. And then the network will basically help you to do the inference. And this will be much faster than running HMC or any other kind of inference method at runtime. So one thing that I wanted to do with Anglican originally is like, oh, can I just hook this into a REST handler in my funny Clojure code and say like, okay, I can do some inference online while the server is running about what people request and what I potentially should prefetch or whatever. Like, you can imagine many things, recommendations you want to send to people, whatever. And it turns out that this is like not fast enough probably, or at least like not the ideal way to do this. So amortized inference, where you train a neural network, or you use some other technique, some function approximator to help you with the inference task when you have to actually perform it, is a very interesting thing that is not yet provided, neither by Renier nor by Stan. So it's something we could definitely provide. It might be helpful for industry purposes, I think. The linear, so the standard library that's provided for the FOPL language is still fairly small, and it's work in progress. I think it would have been cooler at the time. This was not really fully, I think it was either not there yet or it was not fully developed. So just stick to like this emitting of Python code and not actually running it from Clojure. But obviously you could just invoke like the flow training and also the invocation of the resulting artifact that you have trained from directly with like libpython CLJ. This is my complaint about Clojure, or the way I would say like Clojure is not really that well made for compiler building. And I think the ecosystem lacks like, I mean, there's like Psi, the interpreter, and there's like a lot of work going on in static analysis, but I think there are not yet a lot of libraries that make this easy in general to build like new languages and new infrastructure, like really new programming language abstractions. And there are a lot of libraries, like for instance, Turnstile in Racket, that might be very helpful to have a concise notation, or this NanoPass framework, which actually fuses all the passes, so you can have a gazillion of passes and it's still fast. This is work that I think would be nice to have in the Clojure ecosystem. We could have totally a native image or even a ClojureScript compiled version of Daphne, because it's fairly self-contained. I already talked about this. And yeah, in the longer run, if you really want to use it in large-scale production settings, you would have to be able to scale it up to thousands of random variables, which I haven't done yet. And here are some references that might be helpful as a background.